One important application of capacitors is storing energy. Capacitor can store charges, and charges have electric field between them, and therefore they can serve as a source of energy because the electric field can do work on charges. So capacitors are used to store charges. One nice example that we all are familiar with is the flash in the camera. The flash in the camera, you have a capacitor with large capacitance. It is charged from the battery, and when we press the button, there is a discharge there that gives that glow, that brightness, that great light for the flash. To calculate the energy in a capacitor, we can calculate that from the work equation. Work equals minus Q VB minus VA. We know the relationship between V and the Q. It's a linear relationship for capacitors. So you have this linear graph. So now we need to calculate the areas here, delta V, delta Q. This would be the work needed for this segment. You add the work done for this segment, the work done for this segment, and so on and so forth. When you add all these values, you get you get the change in the work, which is equal to delta V, delta Q for each one of these slices. So since we are interested in the area, this is the area for a triangle, which is half the base multiplied by the height. So it is half Q multiplied by delta V. This would be from this graphical solution. This would be the work, which is equal to the energy stored in the capacitor. So to calculate the energy stored in a capacitor, you need half Q delta V. Then we can use this equation for a Q, C delta V, and this way we can solve for the work in terms of the voltage. So it is half C delta V squared, or half Q delta V, or Q squared over 2C, if you substitute for delta V from this equation here. These three equations are identical. Depending on the information given in the problem, you will use the right one in order to calculate the total energy stored in the capacitor. For example, if the capacitance is 5 microfarad and the voltage difference between the plates is 120 volts, the energy stored in the capacitor, half C delta V squared, half 5 by 10 to the minus 6 farad, that's for C. And for the change in voltage, 120 volt squared, this is 3.6 multiplied by 10 to the minus 2 joules. That's the amount of energy stored in such a capacitor. There are many important applications for capacitors. This is just one of these examples. So here it is used to stop cardiac fibrillation in heart attack victims. In this fibrillations, heart produces a rapid irregular pattern of beats. So when you have a charged capacitor that being discharged quickly through the heart muscles, this will force the heart muscle to follow the path of the potential difference as it is going down, and this way this will suppress the irregular beats. A parallel plate capacitor is disconnected from a battery. So when it was connected to the battery, it was charged. Now it is disconnected from the battery, and the plates are pulled a small distance further apart. So now D increases as you pull them apart, D increases the distance. Does the Q increase, decrease, or stay the same? Benjamin, any suggestion? So Q is trapped within the plates of the capacitor. It has no way to go. Whether you increase the distance, you decrease the distance, or not, Q will remain the same, right? Very well. Now, the plates are pulled a small distance further apart. Does C increase, decrease, or stay the same? When the distance increases as you pull the plates apart, the capacitance should decrease. A parallel plate capacitor is disconnected from a battery and the plates are pulled a small distance further apart. Does delta V increase, decrease, or stay the same? As you move them apart, you are changing a few things. You are changing the distance, and since delta V equals ED, E is constant, E is sigma over epsilon naught, but as you pull them apart, D increases, therefore delta V increases. Does the energy stored in the capacitor increase, decrease, or stay the same? You need to check here. The energy Q squared over 2C, Q remains the same, while C decreases. As you pull the plates apart, C decreases. So when the denominator is less, the numerator is the same, then the result here will increase.